Okay, kids, so we're back. Last time we just watched some videos, try to get our minds on this new way of looking at the universe, the quantum mechanical universe, so quantum mechanics. So there were two main changes in the view of the universe. I'm really trying to hit the highlights here as we uh, get close to the end. One of them was the whole idea of wave particle duality that we looked at before. That electromagnetic energy, light, has properties at times that make it seem as if it's a particle, a photon, and has properties at times that make it seem like it's a wave, an electromagnetic wave. And the same thing can be said about matter. Matter has properties that at times show that it's a particle. We can identify its position, its mass, its velocity. But also, matter has wave-like properties called matter waves, and they express the probability of finding a particle following a path as it moves. Now, this doesn't really deal with large macroscopic objects like an apple or a human being. We're talking about subatomic particles and as they travel, interact with electric magnetic fields and matter and such. But uh, that wavelength of matter waves was found. It's actually called a de Broglie wavelength, and it helps us understand the probability of a subatomic particle taking a particular path. So this is earth-shattering for the scientific community that energy and matter both have properties that are wave-like and particle-like. So this really changed things a lot. The other big change that came about was the idea of the quanta, that electromagnetic energy, light, exists only in discrete or distinct amounts. So it's not like here, if you have a particle and you're lifting it up a ramp. So here's a particle, you're lifting it up a ramp, and it can have an infinite number of gravitational potential energies because it'd be mass times the gravitational field strength near the surface of the Earth times its height. Well, the height changes continually. So you have an infinite number of gravitational potential energy in the classical Newtonian view of the world. In quantum mechanics, they started to see back in the day that the energy of a particle only existed in certain allowable possible steps. This was huge. This was the work that was brought forward by Planck. You might want to read about him, kind of an interesting fella. Um, I'll let you read about him if you want. He had some strange positions in his life, but what are you going to do? Next. Well, what evidence do we have that this is actually true? Well, one of the things it was the ultraviolet catastrophe, kind of started everything, and that the energy of light actually depended on the frequency of the light. That wasn't the same for other waves. In other waves, it depended on the amplitude, right? And that's not true here. And that's why things like ultraviolet light has a lot more energy in it than red light or infrared light. Ultraviolet light can burn your skin, all right? Higher frequency. And so the energy of light or of a photon is equal to Planck's constant, might as well name it after the guy who started it all, and the frequency of it. So this was brand new. The energy of a wave depends on its frequency. We thought the energy depended on the amplitude, right? Remember way back in class, we could on the spring we could have little amplitudes or really wave your arm back and forth and have huge amplitudes. This was a huge change. What else came about? The photoelectric effect. Einstein steps up and says, look, if you got light from photons and they hit a piece of metal, if the situation is correct, those photons can eject electrons from the metal, and those electrons will have a certain kinetic energy. And the kinetic energy that they have will equal the energy that the photon had, Planck's constant times the frequency. Look, see, Planck's constant times the frequency, minus W, which is the work function, which is the amount of energy needed to remove the electron from the attraction of being in the metal. And this has been repeated, this experiment, many, many, many times. I've actually done it myself. And wow, this must really prove that the energy of light depends on the frequency, because what they would do is they would shine, let's say, for a particular metal, red light at it. Nope, no electrons escaping. Oh, well, let's make the red light brighter. Nothing happened. Okay, well, what about if we use a different kind of light, like violet light? It could be really dim violet light. Well, really dim violet light might cause a few electrons to be released. Really bright violet light would cause more electrons to be released. But you could have the brightest red light possible. It is not going to release a single electron, because the energy that is hitting the electron depends on the frequency of the light. Brand new. Like, wow. Okay. This is different. The universe is not what we thought it was. Next, the Compton effect in terms of energy. You have light and a photon. We know the energy is Planck's constant times the frequency. It hits the electron, and what happens is the electron takes off with a gained amount of kinetic energy, and there's also some light left over, but it's light of a lower frequency. Look, F prime. And this led Compton to even see that momentum was conserved. Momentum. Light has momentum. Yes, it does. Here's the frequency for it right there. I'll let you read about it in the textbook to see how this equation came about. But when light hits an electron, that electron of a lower frequency that scatters away, and the momentum of the electron that leaves, it's conserved. Wow. Light has a momentum? How can light have a momentum? How can a photon have momentum? It's energy. It has no mass. How is this possible? Well, I'm going to let you kids read about that, okay? And there are other effects as well, but these were the main ones. So once again, I got this video lesson for you here, and I got some videos for you to watch, because it's kind of hard to draw the subatomic and do all the animations in a video, and the textbook to read. Okay? So, like I said, I'm just trying to make sure that when you see this next year, that it'll be, that's Zafiro. All he did was say, "What's up, G?" He didn't teach us anything about quantum mechanics. I don't want that to happen. I want you at least to have an idea of this idea known as quantum mechanics, this new way of looking at the universe. That's our main goal here. And I think if you read the textbook, go through my video lessons, watch the videos that I show you. So it's not like I'm giving you homework, kids. I'm really taking my foot off the accelerator because you guys have been awesome. But just so you have an idea of what this is for next year. Okay, have a great day. Bye.